Thanks everyone for coming to my talk. I know it's late in the afternoon, and I think it's just me standing between you and maybe a beer or something, or in dinner. So I'll try to make this interesting. I'll try to make this casual, and hopefully it will make it worth your time. All right, thanks everyone. We're going to talk about putting RAGs into production with LanceDB and DBRX. But my name is Chung. I'm the CEO and co-founder of LanceDB, the database for multimodal AI. I've spent about 2 decades building tools for working with data for data science, machine learning, and AI. I was one of the original co-authors of the Pandas library, if you've used that. I've spent a bunch of time doing big data systems and also recommender personalization systems. And I'm now working on LanceDB. These days, I spend about equal time tweeting and coding. And if you want to generate that chart, you can go to shiptalkers.dev, and you can put in your Twitter handle and GitHub handle. So I think we're going to talk about RAG today. How many of you have not heard the term RAG? Okay, awesome. How many of you have built a RAG POC? And how many of you have put RAG into production? Right, that's the proof of this slide, right? Almost everyone's built a POC or a demo for RAG. Very few RAGs make it into production just because it's much harder. So, and just sort of to show you how, and you've probably seen the text ones, where you can just show you how to easily build POCs to illustrate the point is this example that you'll find from LanceDB. We call it vector DB recipes. Using Hugging Face, Databricks, DBRX, and then Llama Index and LanceDB. It's about, what is that, like 10 lines of real code. And we can put together a little Streamlit app that essentially puts together LanceDB with DBRX and Stable Diffusion. And what it's doing is it's ingesting the Harry Potter wiki website, and then you can do Q&A off of that. So you can say something like, what is Hogwarts? And it's going to fetch the relevant documents from LanceDB on Hogwarts, and then it's going to use DBRX to generate the answers, and then it'll illustrate the response using Stable Diffusion, or you can say something like, how do you play Quidditch? All right, and so you'll get a pretty detailed answer here on the different positions and how you play, and that's actually pretty good. And it's generating an image that looks like what the answer might be talking about, even though it's not quite right. So building these demos and POCs is actually quite easy, and you can build things that seem pretty compelling fairly easily. But putting it into production is not as easy. So this is a typical RAG workflow. The incoming query will retrieve the relevant context, will augment the prompt, and then pass it off for generation. So a specific one might be something like, why did operating expenses rise more than expected last quarter, right? So if you want something that's in production, it's going to talk to your private data, and you want it to be extremely useful. And it's a little bit cut off by the captions there, but supposedly in your vector database you have financial reports, you have spreadsheets from your FPGA function, you have maybe slides of presentations that folks did. Once you retrieve the relevant context, the prompt becomes answer the question, why did operating expenses rise more than expected last quarter, given the context that you retrieved. Right, of course, and then you call an LLM to generate this, and then you get an answer back, something like, the 2 biggest factors that contributed to the increase were, blah, blah, blah. Okay, so problems for doing this in production. Number one is scale. Number two is the quality of that retrieval. Number three is reproducibility, debuggability. Number four is data privacy. And then number five is vendor lock-in. So these can all affect how easy it is to put your RAG pipeline, your RAG application into production. All right. So number one is scale. All right, so scale, especially with AI and with multimodal data today, it's much bigger than before. Right? If you look at a tabular data set, roughly each row is about 145 bytes. If you add embeddings in there, it becomes about 20 times larger. If you have images or videos, they become extremely large very quickly. In addition, with AI, instead of just having your data being manually collected and manually labeled, they're now being automatically generated at thousands of tokens per second. So you're not constrained essentially by the scale of human effort here. Okay, so to deal with that scale, right, you'll probably need a vector database. And then because you have so many vectors and all of that data, you're storing that in a data lake, and you probably have to load that into your vector database. This process at scale is complicated, it's slow, and it makes it very expensive because you got to hold all of those vectors not only in your data lake, but also in memory in the vector database. Right? And so if you look at a hot off the press blog from Ben Lorica and Prashant Rao today, they talk about when you put vector databases and vector search into production, what are the key features you want to be looking at in production? In particular, with scalability, you want to talk about horizontal scalability or serverless scaling, and also separation of compute and storage. And all of these things not only make it possible to actually scale out your operations, but also make it cost efficient to do so. Okay, and then let's talk about quality. All right, so it's very easy with pure vector search to get to somewhere around like 60 or 70% quality with your RAG application. But in order to get to production, you need that extra sort of 10, 20, 25%. And so what do we do? Experimenting with chunking strategies, we can play around with the embedding space, with fine-tuning your embedding model. And one big one here is actually using more than just vector search. So we can use full text search, for example, and not pictured here is potentially using a graph database to do graph search, and then putting the results together in a re-ranker and combining the results. Right, so different retrieval modes really help. And so when you have hybrid search, then you have a re-ranking process, and you can plug in different re-rankers. And then fine-tuning the embeddings once you have user feedback. And sometimes, even when you don't have user feedback, a synthetic data set can be equally as useful to bootstrap your fine-tuning process. And so when you have so many different things that you can experiment with and put together, the composability of those tools and the customizability of those tools becomes super important. Okay, problem number 3 was security, privacy, right? The RAG context that you retrieve is extremely valuable. So if you think about it, models are still advancing quickly, but they will commoditize. And I think we're already seeing a plateauing of the improvement in quality in models. So ask yourself in a year or two, if models are commodity, how do you differentiate your enterprise from others when you're building that AI application? Well, the answer is data, right? So just like it is in pre-AI days, data is still the differentiating value, the secret sauce for your company, for your team. So your most prized asset then should stay on premise, should stay private. But with a lot of RAG pipelines today, that's not the case. right? It's often easiest still to build RAG pipelines to start with calling third-party APIs for embedding generation and also for LLM. So when a user query comes in, you now you call out to embedding model. So now your searches are leaving the premises, right? And then you have the vector database that you're using to then retrieve that context. And then when you send the augmented prompt to that third-party LLM, you're now sending potentially your very private data out in the public open internet. And so once you do that, you often have no control other than promises that it won't end up in training data. The last problem is lock-in, right? Long-term flexibility is super important to be able to move your data from system to system, to be able to migrate easily, and to be able to evolve your data stack and AI stack in a way that is fitting for the stage of AI application that you're building, right? So, for example, storage should be open. So if you dump vectors into a system and you dump your metadata, it shouldn't just go into a black box. It should be easy to move that into a different system or move that back into your data lake. And instead of having this walled garden, you want to not just have one workload that you can run on your vector data, right? It's not just searches, but the full text indexing, SQL, and if you're using your data for training, that's a whole separate set of compute that you're going to want to be able to run. RAG components, right, should easily be swappable. Maybe you chose a vector database to start that was based on ease of use, but then once you get to scale, you want to swap it out, and maybe you want to have different re-rankers and be able to have increasing levels of sophistication, and you don't want to have to fundamentally change your data stack anytime you want to change something about one component of that system. Okay, so basically the problems with this is at different points in your pipeline, the common ones that you build to start is often not very private and not very scalable. Instead, in your data lake, we can now use LanceDB, and also you can use DBRX to sort of keep everything on premise. So LanceDB is a database for multimodal AI, and vector search, scalable vector search is one of the main features. It comes with a built-in embedding registry, and you can write to Lance directly using Spark or Ray or other distributed engines through its Apache Arrow integration. And of course, I'm sure you guys have heard lots about DBRX in this conference. It's a great new LLM for you to use within the Databricks ecosystem here. And so with Spark and LanceDB, you have distributed writes. You're not sending small batches to a HTTP API for your vector database. You can ingest the internet very quickly. And with the built-in embedding registry, you can swap in third-party APIs with open source models or build your own very easily. And then with DBRX, your generation also stays on-prem and stays private. Okay, so just a little bit on LanceDB itself. So we're the database for multimodal AI, and we're based on a format called Lance. And so our tagline is, at LanceDB, we Lance a lot. So the number one thing about LanceDB is you can scale to sort of galactic scales very effortlessly. So in production, LanceDB works in enterprises serving billions of vectors in one table at more than 10,000 queries per second, and at 10 gigabytes per second of transfer. with high recall, low latency. And it's also doing that with an order of magnitude more efficiency than alternatives. And we'll see why in a second. And the reason why we call LanceDB the database for multimodal AI is that, well, it is truly a multimodal database. And it's multimodal in several different ways. One is it can store multimodal data very effectively. So now, of course, an embedding is just an embedding, but you can't serve embeddings back to your users. So you need somewhere to store your images, the audio waveforms, or the video. And traditional datasets, data systems can't do that along with your tabular data and vector data. Queries can also be multimodal, right? So vector search, full text search, SQL, hybrid search that combines multiple modes, and then re-ranking after that. And lastly, the type of workload can also be multimodal. So not just search, but exploratory data analysis if you want to filter images or say, find me 10 images most similar to the one that I'm pointing at that has exactly 3 people in it, right? You need to have a system to be able to do that. And for training, if you're doing pre-training or fine-tuning, you need to be able to filter your data, curate your data, and then feed it quickly into a PyTorch data loader. So, and LanceDB gives you that capability sort of in a very simple single source of truth. So with the same table, you can store strings, categorical data, time series data, and then your actual content, maybe it's a video, and then the embeddings that are generated from those videos, for example, so that you can do things like, this doesn't seem like it's working. Okay, well, if you look on the right-hand side, you can run SQL queries to search for particular pieces of content based on metadata filters. You can plug your data into a PyTorch data loader to do training on the videos themselves. And of course, you can run similarity search and vector search on the vector column that you've generated. And all that happens within one table without you having to copy data from one place to another and without you having to coordinate between all of them. So the secret sauce behind LanceDB is not so secret. It's actually open source. It's called Lance Format. And it's core to LanceDB, and it's really optimized for AI data. So what Lance Format solves is what I call the new CAP theorem for multimodal data. And what that means is traditionally with OLAP SQL queries, you need fast scans. That was pretty much the only requirement. So Parquet and Friends are very optimized for that. But if you now start needing to do things like searches or shuffling when you're doing training, now you need to be able to support random access as well, and Parquet does not do that. And then if you need to do distributed training, you also need to be able to manage large blob data. So if you're storing images or videos in line, you need to be able to efficiently stream that from cost-efficient object storage to your GPU to, one, keep your GPU utilization high, but number two, without having to cache all of the data on very, very expensive storage, right? So no system, in no format, no system is good for all three. And that's the reason why we decided to make Lance Format, right? So, and not only that, the Lance Format also comes with an indexing subsystem. And so we can use that to speed up filters even more. And then we also build lots of different types of vector indexing to support fast vector search. And lastly, the Lance Format gives us a way to do schema evolution. So if you're experimenting with your RAG pipeline, or if you're experimenting with fine-tuning, you can add features or you can add new vector columns without having to copy the old data and without having to throw away the old data. And you can search on multiple vector columns as you like. And these things are essentially automatically versioned. So if you find that you've messed up, you can always instantly roll back to a previously good state. Right? What Lance format allows us to do is separate storage from compute. So your index now can be served from disk, requiring little memory. The data can be shared without having to tie together your the vector storage plus your compute. So this allows us to scale very efficiently. And we've now unified exploratory data analysis, vector and full text search, and also these distributed training workloads. Okay, cool. So I think we're coming to the end of the talk, right? So remember, RAG in production, right, comes with a lot more new challenges that you don't really see when you're building that POC. Whether it's scale, the quality, and privacy of that data, and then vendor lock-in. All of those things you need to consider if you're trying to take a RAG application into production. So I hope I've proven that LanceDB is great for these use cases. It's open source. You can use it to build a composable RAG pipeline. Everything stays on premise so that your most valuable assets aren't going out to the open public internet. And it's able to deal with hyperscale at about order of magnitude more efficient. Okay, awesome. All right, I guess it's beer o'clock, guys. All right, thank you so much.